Okay, so in this video we're going to integrate this function here, cosine x divided by 5 minus 4 times cosine x with respect to x from 0 to 2 pi. Okay, so u sub for cosine x, that'll be u over 5 minus 4u, very difficult. Find some other thing, let u equal 5 minus 4 cosine x, not going to work. Integration by parts, definitely not going to work. So what we're going to do is, we're going to go through complex analysis. So we're going to change all these values into complex values with z. So what we do is, to change cosine x, we'll call cosine x, so we'll make the substitution half z plus 1 over z. Okay, and then the dx, we change that to 1 over I z dz. So, and then the 0 to 2 pi, now if that was a parametric transformation for the unit circle, what we would say is that gamma would be 0 to 2 pi, so basically it goes from, let's just write this down on here, 0 to 2 pi, and the actual gamma itself is e to the it. Okay, now this here is just the unit circle where z equals 1. Okay, so that's what that is. So now we'll just transfer all this into here and go from there. So we go from 0 to 2 pi. So now what we do is we just say it's on gamma. And then cosine x is a half z plus 1 over z. And then we divide all that by 5 minus 4 times cosine x, which is this. And then for the dx, we put this information in. Okay, close the bracket. Okay, that's a big change from here. Now we're into complex numbers. So we got z equals x plus iy. Okay, this is a half here, not a z. So very important not to mix that up. Okay, so what we're going to do now is just to do some algebra on this and just try and get rid of some of these fractions, this iz on the bottom here. Let's see what we can do. So what we can do is now we change on gamma, 1 over iz, and we've got a half here. So the half and the I, maybe we can bring that out front. So 1 over I is minus I, and a half is constant multiple. Let's bring that out to the front. So now that takes care of this, and it takes care of this I. But we're still left with this z here, and this z plus a half. So let's leave the top as it is for now. Z plus 1 over z. And let's distribute this z into these bottom terms. So if we multiply everything here by z, we end up with a 5z, and then a 4z here, which will then distribute through all this. But while we're at it, we get rid of this half, so we call it a 2z. So that's minus 2z, and then z plus 1 over z. And that's all dz now. So now we've taken care of this, the I is out the front, and the half is here. Okay, so we're still a bit awkward on the top here with this 1 over z. So if we multiply that by z, we get that z times 1 over z just gives us 1. So that will become z squared. But then if we multiply the top by the z, we have to multiply the bottom by the z. So let's go again. Integral on gamma, multiplying by z. So z squared plus 1. And then multiply this one here by z, and this one here by z. So we'll have to multiply both terms by z. So we'll end up with z, 5z minus, now instead of multiplying this by z, let's multiply this one by z. That way then we get this 1 over z term to get removed. It's minus 2 over z, z squared plus 1. Okay, let's do some algebra on this and see what we can get to now. Oh, don't forget the dz, of course. So now what we get to now, so this is now minus I over 2 integral gamma z squared plus 1, that's absolutely fine. And then we end up with z times 5z, so that'd be 5z squared minus 2z cubed plus 2z, but it's not going to be plus 2z, it's going to be a minus, so this will be a minus. Okay, and again the dz is here. So let's take this all the way up to the top. So minus I over 2 integral on gamma z squared plus 1 dz. Right, so what are we going to do with this now? So we can take a z term out, factor the z out, let's see what happens there. So then we get z, 2z squared plus 5z minus 2. But then we've got this z cubed here is a minus 2, so bring minus 2 out the front. Okay, let's go again. So now we've got minus I over 2 integral on gamma z squared plus 1 dz stays there. Let's see if we can change these around a little bit. So that minus 2 and this minus 2, I'm sure there's something we can do there. So sorry, minus z, sorry, that's not a 2, it's a z, sorry. So let's get rid of this minus and just call that z, and then we'll change things around a little bit. So we'll have a 2 minus 5z minus 2z squared. Okay, so if we factor this out, we're going to get a 2z and a 1 and a 2z and a 2, sorry, single z and a 2. So let's just have a look, see what we can get to there. So on gamma, z squared plus 1 dz. And then what we'll end up here with here now is z minus 2z and a 2, so we want a 2z plus 1. So 2z plus 1 taken out of that, that's just going to leave us with a z plus 2. 2 times 2z is 4z, and that will leave us with a z plus 1, so that'll be plus a single z, so that'll give us our 5z, z plus 2. Okay, right, now just put this in a box here. Just want to take you to a video I did previously where we found the residue of a function very similar to this one. So z squared plus 1, 2z plus 1, z plus 2. So we've got the same function here by starting from this, doing all this algebra to get to here. So what we found was the residues of this function were as this. So if you follow the link down below, you'll see how we got to the residues of this function. So now what we can do is we can say that this here is a closed contour on a simply connected region, which is obviously it's in the complex plane. So what we can do, we can apply Cauchy's residue theorem. So with z equals 1, so that's our circle, z equals 1. Our residues here are minus 2, so that's minus 2, minus 1/2, and at 0. So with Cauchy's residue theorem, what we can do, apply the values of the residues that are inside our value here that we're given, and ignore this minus 2 one, and then we just multiply them by 2 pi I. So Cauchy's residue theorem, so we multiply 2 pi I by the residues of f minus a half plus, let's just take that off there now, don't need that now, residue of f at 0. Obviously those are the 2 points that are in there. The minus 2 we're not interested in. That doesn't count for us. Okay, so let's take this off there now. Now one thing just to be careful of with the integral here, we also add a minus I over 2, which is constant multiple. So we need to bring that out the front of this calculation as well. So we've got minus I over 2 times 2 pi I times, open brackets, residue at minus a half is minus 5 over 6 plus, and at 0 it's 1/2. Okay, now we can do some simplification on this. Now we should get a real answer because we started off with a real integral, so there should be no i's in what's left. So we can see here there's 2 i's here which are multiplied. Well, I squared is minus 1, but then there's a minus sign here, so it's a plus 1. So those i's basically cancel out, which is basically what we wanted. And the 2 pi of the 2's cancel out. So it's pi times, right, minus 5 over 6 plus a half. Let's just do that quickly. Minus 5 over 6 and a half over 6 is 3 over 6. So that equals minus 2 over 6 minus 1/3. Okay, so now multiply this by minus 1/3. So therefore we get our answer as minus pi over 3. That's the answer to this integral. Starting off from a real integral, using complex analysis and the residue theorem, get our answer. And when we first looked at that, it looked really horrendous to try and integrate that function. So by using some simple algebra and minus pi over 3 is our answer.